Well, welcome back to zoology. I hope that everybody's doing fine and, of course, that you're in a good, safe environment. I think I found a way to be able to narrate the PowerPoint slides, and I hope to help you out. For lecture exam 3, we covered some of the information already that you'll see on the PowerPoints posted on the portal that was taxonomy related. Then we started to look at, I think, chordate diversity and chordates overall, and it would have ended at about this point, which is the last PowerPoint lecture that's posted on the portal. And this is the one where I thought you might benefit the most if I could narrate it a little bit. I think the other PowerPoints on classification you'll be able to do on your own just fine. But what I'd like to talk to you about are some of the unusual traits. Before I go on, though, let me tell you about this particular animal that you're seeing pictured right now. This is called an amphisbaenid. A-M-P-H-I S-B-A-E-N-I-D. That's just in case anybody would like to look it up on Google and learn more about it. They're an interesting critter. They live in the North America. They live in the Americas. I think down into Central America as well. And those who I've known have kept them in captivity to learn more about them haven't been able to get them to live much more than a year. Maybe some places have, but interestingly, I've never seen one in a zoo and never one in the wild. Okay, back to the point. I think we're ready to start talking now about these characteristics that I wanted to help you understand with a narration. Here we're taking a look at a bunch of turtles. I'm going to guess that most of you have seen turtles like this. Here's a fun question for you. If you saw turtles basking at about 9 o'clock in the morning on a log in a pond, which side of the pond at 9 in the morning do you think the turtles would be on? So north, south, east, and west are your choices. Well, if you think about it, and the point of the slide, what the turtles are trying to do is capture some of the heat from the sun. And so at 9 in the morning, they're probably going to be lined up on the west side because the sun's coming from the east in the morning. In fact, I've gone out fishing before and seen turtles all lined up on logs just like you can see them here. And I've gone out in the morning and noticed them on the west side, and then as I come back in towards the evening, they've all shifted to logs on the opposite side, and it made me think about them positioning themselves. Maybe you've seen people do this who are trying to get some kind of suntan or something. In any case, what these turtles are doing and what the point of the slide is that we're seeing thermoregulation. Turns out that other reptiles would do this as well, and here in the upper right corner, you can see an alligator doing this with a great big turtle. And I think that turtle being big is part of the reason they can do that together. One of the fun things, by the way, about alligators and turtles is that they do something that I remember learning when I was a little kid, and I'm sure you guys know to do this. Imagine that it's a cool evening and you're all tucked nicely sleeping in your bed with the covers all up, and you start to get a little too warm. Maybe some of you will stick your foot out from under the blanket and that'll cool you off a little bit. Well, that's exactly what turtles, and I'm going to go back to the last slide, turtles here will do, as well as then alligators. They'll actually start to get a little overheated, but the water might be really cold, and so they don't want to make the full plunge into the water. Instead, what they'd like to do is to be able to cool down just a little bit. So what they're probably going to be able to do is stick that foot in the water and cool down like you might do when you're too warm underneath the covers. Well, when we think of thermoregulation, we also need to pay attention to animals that aren't reptiles, and that would be mammals. We're talking about vertebrates here. And here what we see are both birds, and which are reptiles, the type of reptile, and mammals. And what we see is that they have very good insulating coats. Now, if you really think about it, other than birds, reptiles don't seem to be well insulated. When you think about mammals, you do think about fur and you think about something that does provide insulation. So here we're taking a look at some animals, the polar bear certainly and the penguin, that are both in very cold environments. And so why the insulation? And the answer has to do with the source of heat. Here, although they are getting some warmth from the sun, both the polar bear and the little baby there on top of mom is getting heat also from mom's body, and the penguin are both capturing some of the energy from the sun. But even when the sun's down, they're still able to stay warm because they produce their own body heat. And then that brings us to the terms. Ectotherms, like the turtles and the alligators and amphibians and almost all fish, they get their heat from outside the body. And that may come from the temperature of the water that they're sitting in, or it may come from the air temperature, it may come from resting on warm rocks. In the evenings after the sun sets, sometimes in the spring, reptiles will go and sit on a rock that's still warm from the heat of the day. Or it might be the sun for ectotherms. Endotherms would then be the mammals and also birds. And so what they do is they have an insulating coat to try to keep that heat in. Well, maybe you've heard of the terms cold-blooded and warm-blooded, and we aren't going to be using those terms here in zoology because we're actually breaking this thing down a little bit more between ectotherm and endotherm, and then these pairs of terms, whether or not they're homeotherms or heterotherms. So when you think about those terms, do you have a steady body temperature or does your body temperature fluctuate? Well, if you think about a typical mammal, so think about your dog or your cat that's in your house maybe with you, or yourself. Of the four terms that are on the screen, ectotherm, endotherm, homeotherm, and heterotherm, what applies to you? What are you? So when you look at endotherm or ectotherm, you're an endotherm. When you take a look at homeotherms and heterotherms, well, we hope that you're a homeotherm, that you have a steady body temperature. Now, if you get sick, oh my gosh, that you get the COVID-19 disease, then your body temperature might fluctuate a little bit. But if you really think about it, and let's just use Fahrenheit to make this maybe a little easier. If your body temperature is about 99 normally, and you have a fever all the way up to 103, that's a 4-degree increase on 99 degrees normally. 98.6 rounded up is 99. Well, that's about a 4% variation. And above a 103 fever would probably cause some real problems. So 103 is already getting up there. So we, as homeotherms, really don't allow our body temperature to fluctuate much at all. And even in a feverish condition, my point was, it might increase by only 4%. Heterotherms could see their body temperature in Fahrenheit vary by as much as 30 or 40 degrees Fahrenheit in the course of a day. If you think about a frog, a bullfrog sitting on the bank in shallow water in the summertime, maybe in the spring when the water's still cold, that frog could really heat up into the 70s and 80s in Fahrenheit. But then if it dives deep to escape perhaps a dog or a cat running along the shoreline, that bullfrog diving deep in the pond might go from 80-degree air temperature and shallow water temperature to easily 50-degree temperature near the bottom. And so that bullfrog would be a heterotherm. Okay. Now let's think of some of the exceptions. Why is it that we zoologists are not that fond of cold-blooded and warm-blooded? So I think, actually, let me go back for a second. What of these terms would you say are typically associated with being cold-blooded? So when people talk about cold-blooded, would it be more an ectotherm or an endotherm? And I hope you're thinking ectotherm. And then when you think about a cold-blooded animal, again like that bullfrog, are they a heterotherm or a homeotherm? And I hope you're thinking a heterotherm. Okay, so humans are more endothermic homeotherms. A bullfrog would be more an ectothermic heterotherm. And now that brings us to the exceptions. So we get something here that's really kind of interesting. If we take a look at the hummingbird situation, and hummingbirds will be returning to our area very, very shortly. In fact, about the time that you take your lecture exam 3. You want to check that schedule that I sent out yesterday, of the 24th of March, and take a look at all those dates when we have our online live quizzes or exams. So I'm counting on everybody to follow that. Well, if you take a look at a hummingbird that, again, probably returning here to our area, Illinois anyway, about the 15th of April. On the left side of this diagram, you see a hummingbird that's just eating and feeding fine during the course of a day. And with all that food, that's plenty of energy. The hummingbird's very active, and it has no trouble having a high, steady body temperature generated by its own heat. So if it's a high, steady body temperature generated by its own heat, what are the two terms that we would associate with the left side of this diagram for this hummingbird? And I hope you said a homeothermic endotherm. But now take a look at the right side. If, at the bottom, it says if nectar is adequate, then during the evening, the hummingbird, while it's resting, may maintain its high body temperature. Here, we see it in Celsius, 39, so that's even higher than our core body temperature, which is about 37. But if you see that if nectar is scarce, and that could be the case when these hummingbirds first come back, my goodness, they've migrated perhaps over 1,000 miles of this little bird flying to get back to Illinois. That's why I like to have my hummingbird feeders out right away in April. In any case, if they get back and there are not a lot of flowers for them to feed on, then in fact, the top conditions, top right, are probably what's going on. Nectar is scarce, there's torpor, and the body temperature is going to drop at night. So it raises the question. Overall, throughout the course of a year, if you think about a hummingbird, what's the term that best applies? Well, they're endotherms, but are they homeotherms? Well, on the bottom, with plenty of nectar, yes, they're homeothermic endotherms like a mammal. But up at the top, you see the capacity for a homeothermic endotherm to actually sometimes be a homeothermic, an endotherm that is a heterotherm that allows its body temperature to vary even though it's an endotherm because it produces its internal body heat. So I'm going to clarify that. At the top right, instead of being a homeothermic endotherm, it's a heterothermic endotherm. Okay. And so the answer, what term applies to a hummingbird that goes into torpor, what terms apply, and it's an endotherm still, but it's a heterotherm. So go back a slide just to review what those terms were. When a hummingbird lets its body temperature drop, it's still an endotherm, but it technically is a heterotherm. Okay, now going ahead. Here's another situation. Fish normally do not control their body temperature by generating enough heat to maintain a steady body temperature. Most fish, whether in the ocean or in freshwater systems, maintain the temperature of their environment. So if the water's cold, they're cold. So if they're getting their heat from outside the body, are they ectotherms or endotherms? Well, they're ectotherms because they're getting their heat from outside the body. But lots of bodies of water maintain their temperature. They don't change quickly. I don't know if you've thought about that. But if you go to the ocean, let's say, and you have a chance to swim in an ocean or a chance to swim in a lake, and you go in and you have a fun time and hope the water's not too cold, and then you come back the next day, is the water radically different temperature? And the answer is no. It has to do with something called thermal inertia. And with thermal inertia, the tremendous mass of large bodies of water, could be freshwater, of course it's the oceans, these systems cannot change their temperatures quickly. It would require an incredible input of heat. And therefore, oceans and large lakes, like the Great Lakes, tend to maintain a steady temperature. Over the course of a year, yeah, they might fluctuate a few degrees. Maybe even more if it's a great lake like Lake Superior. Might change, who knows, Fahrenheit, maybe 10 or 15 degrees Fahrenheit. But if we think about tropical marine systems like we're looking at, this is a temperature that's not going to change much. So this is another exception. Are they endotherms or ectotherms in this tropical marine ocean environment? Well, they're ectotherms. But does the body temperature fluctuate a lot? No. So they're ectotherms and they're homeotherms. So ectothermic homeotherms. And that now brings us, one of the reasons I really wanted to narrate this for you, to a very unusual case. We're going to spend a lot more time as we go through this course, mostly for the next lecture exam, and I'm going to talk to you about the importance of size. We won't spend a lot of time right here going through it. So I just want to tell you the principle, and then we'll help you to understand the principle later. As an organism gets bigger, and here we see a human compared to one of the giant sauropod dinosaurs. They have one of these, by the way, mounted at the Field Museum in Chicago. Not a good time now to go there, but maybe you can see pictures of it if you go online. As any organism gets bigger, of course its volume, its mass is increasing. That's what we mean by bigger. But the surface area of the skin, all the skin, even the bottoms of the feet, everything, that surface area is also going to get bigger. Okay, so bigger people need bigger sweaters. Okay, but it doesn't increase as fast as the volume. The surface area does not increase as fast as the volume. So this is a much bigger critter, and it has proportionately less surface area. If you think about this then applied to dinosaurs or anything big, if they're an ectotherm, they're going to gain or lose heat through their surface. You do this. A lot of your heat in the summertime is lost through your skin. You also lose a lot through your breath. I don't know if you ever thought about it. You breathe in cold air, you breathe out warm air, so you're losing body heat. But in the summertime, we don't lose so much body heat because the air is already pretty warm. So we tend to lose heat in the summertime through our skin. Well, dinosaurs, if they got too hot or too cold, or if there's some temperature and now the environment, the air temperature drops, for example, in the evening, they would then cool off through their skin. So let's imagine this giant sauropod in front of us at noon or in the afternoon, and it's a sunny day, and the animal's really getting heated up by the sun. And now the air temperature drops pretty fast at night, maybe even 20 degrees Fahrenheit it drops at night. How quickly will this dinosaur cool down? And the answer is that when we think of the largest land animals like these sauropods, they're so big that they cannot cool down much during the evenings when the temperature cools. And they can't heat up too much in the afternoon when they've got sunshine. And so the point of gigantothermy is that when you're a giant, and that's what the giganto is referring to, you can't considerably heat up or cool off in the course of a day. So what they are, the giant sauropod animals, is they're ectotherms, but they have a steady body temperature. And so what term are we talking about for steady body temperature? And I hope you're thinking homeotherm. So gigantothermy is that when we have the largest terrestrial animals, they will not heat up or cool off considerably in the course of the day. They're just too big. They don't have enough surface area. Now today, the largest of all the animals on Earth is a blue whale. Now, blue whales make their own heat, and they also live in an environment with pretty steady temperature, although when they dive really, really deep, they encounter cooler water. In that particular case, they don't have that much surface area either, and so for them, being so big, they can't cool off if they're really, really active too easily. And so it turns out that in some marine mammals, which is what a blue whale is, these animals have to have special adaptations to cool off. A very active dolphin, dolphins aren't that big, but a very active dolphin has special adaptations to actually get rid of heat, special ways to get rid of heat because they don't have that much surface area. So gigantothermes represents ectotherms that are homeotherms because they don't have the ability to cool off considerably or heat up considerably in the course of a day. All right, different subject altogether, but it's related. When we think about cells, so you know that animals are multicellular. It was one of the characteristics that we talked about. When we look and consider animals and their cells, I have a few questions. Are the cells of an elephant larger than the cells of a mouse? So do we make animals bigger by increasing the size of their cells, or do we do something else? And by the way, are there cells that are huge, the size of a grapefruit? And so if there isn't, what limits cell size? And that's what I'm going to talk about. Now, technically, an ostrich egg, so one of the biggest birds today, we had bigger, and if you went to my New Zealand talk, you learned about the moas, which were even bigger, and their eggs were even bigger. But an ostrich egg is about the size of a cantaloupe, like you might eat the orange flesh cantaloupe. Sweet, I hope, cantaloupe. Technically, that is one egg, but the functional part of the cell is really a small, tiny spot. So technically, it is an egg, but functionally, it functions still as a very small cell. Okay? So when we think of what limits cell size, the first clue has to do with daycares. And some of you may know about a daycare, and you may know that the number of kids that they can have at a daycare is limited by the number of the adults. And that actually has to do with the age of the child. So maybe some of you know if the children are infants, so if they're under the age of 1, then the number of children you can have under the age of 1 is quite limited per adult, trained adults, licensed adults. But if kids are much older, then one adult can handle more. In any case, there's a limit to the number of kids based on the supervisor. Well, if you think about cells, what's the supervisor in my analogy? And if you guessed the nucleus, you would be right. So the nucleus doesn't grow in size. The cells get bigger or smaller, and an individual cell in your body, like a muscle cell, can grow larger or smaller. But the nucleus itself doesn't increase in size. It's the cytoplasm. So one limit of cell size, and here is a very, very large cell. I was just talking about muscles. So this is a skeletal muscle. This is the one that makes your skeleton move, so it allows you to bend your arms and legs and run and do all that good stuff. When we take a look at the skeletal muscle cell, if you know already, perhaps, skeletal muscle cells are the largest by far of all the types of muscle. So we have cardiac and smooth and skeletal muscle. They're also just really, really big cells in our body. Well, how is it that they can be big? Well, how could you have a daycare with a lot of kids? And the answer is you'd have to have a lot of adults. Well, when we take a look at skeletal muscle in our body, they have a lot of nuclei. So that suggests, back to the whole point of this slide, that one limit of cell size is the ratio of the ratio, just like we had a ratio of adults to kids in a daycare, the ratio of one nucleus to the amount of cytoplasm. And we call that the nuclear to cytoplasmic ratio. So to get really, really big as a skeletal muscle, you're going to have more nuclei. And that's an unusual characteristic of skeletal muscle. Another reason that cell size is limited has to do with, well, commuting or the movement of materials in and out of a cell. So let me ask you this question before we go further. Do you know anybody that commutes every day from Carlinville to Carlinville? Well, I do, kind of. I know other people that live in Carlinville. Maybe you know Dr. Morin, who teaches math. He lives in, and Dr. Boama, both in the math department. They both live in Carlinville and teach a course at Blackburn. Did you ever know of anybody that lived in Carlinville that commuted every day to Springfield? Well, my next door neighbor does that. Do you know anybody that commutes every day to Chicago from Carlinville? Well, for those of you that live closer to Chicago, you know that that would be a heck of a commute. It's about 250 miles to get to Lakeshore Drive from Carlinville. I've driven it often. That might be a 4-hour trip. Well, if you're going to and from, that's an 8-hour day of commuting. So you might think about it and realize, well, if this distance that you're commuting gets too great, then it's not very efficient. And that's why I'm going to guess that nobody knows a person that commutes every day from Carlinville to New York City. That would have to be a very, very fast private jet. I guess that's about the only way you could do it. Well, what does that have to do with cell size? If we take a look at the surface to the deepest part of the cell, the center of the cell, that's the maximum diffusion distance. Gosh, if only we had a term for the distance from the center of a circle to the surface. And I hope you're thinking of the word radius. Yep, so that's the radius. And as we make cells bigger, the radius gets even larger and larger. And so as you make that radius larger and larger, it becomes like the commutes to Chicago and New York City. Oxygen from the outside needs to make its way in, and the center of the cell needs to survive. It needs oxygen too. And CO2, you know, is produced by aerobic metabolism, and so that's got to diffuse out. So to keep the middle part of a cell alive, well, goodness, you're going to have to limit the size, because otherwise it just takes too long to get the oxygen in and the carbon dioxide out. And those are only two of the things that have to move from the surface to the center. At the upper right, we see red blood cells. Red blood cells are very unique. You probably know that they're transporting oxygen. They transport a little bit of carbon dioxide too, mostly oxygen. And here we see that the shape of red blood cells is a biconcave disc, which I believe is an adaptation that helps out with this diffusion distance. So by being flat like that, squeezed in the middle like that, so it's kind of like a donut, but it doesn't have a complete hole, then the maximum diffusion distance is greatly decreased. So there's two limits of cell size. Here's the third. So we can consider a couple of baseball stadiums. On the left is the old Busch Stadium that they tore down to put up the new Busch Stadium that looks an awful lot like Wrigley Field. And that's okay. Those of us who are Cubs and go to the Cathedral and get to see baseball played like it should be with a real field. In any case, the Cardinals now have a stadium like this. Well, what's the point? The point is, if you've ever been in a big stadium like this, or maybe you went to a really big concert or some other event with 10,000 people all in some great big area, or even more, so these stadiums can hold upwards of 30,000 people. If it's an exciting baseball game and pretty much everybody's staying to the end, and now the conclusion of the game happens, especially if the home team loses, then everybody pretty much wants to pile out of the stadium quickly. I think if they were winning, you'd probably stay. But if they lose, and I've been there, and I've watched them lose, then everybody wants to pile out. And the problem is they don't all leave quickly. Now let's compare that to when we were in Olin Lecture Hall. When class was over and people wanted to leave, some of you used the stage door behind me, some of you used the regular hallway door, and some of you just took that other door straight outside. And the point is that with our class, we can easily all get out of the room. Why? Why is it so different about the speed of exiting a stadium? And it has to do with the surface to volume ratio that I was talking about when I was talking about gigantothermy. As anything gets bigger, as you take a room like this, like an Olin lecture, made it as big as the new baseball fields, and the new one at St. Louis or Wrigley, or wherever else you watch baseball. If you take an area and make it that big, that's a huge volume then, but the surface area doesn't keep up. So the gates, the exits, are insufficient for the number of people that are trying to leave, and we get all backed up. So, we talked about the first two already, and this third is surface to volume ratio. As cells get bigger, their surface area does not increase as fast as the volume. And so, just like the number of people that can be in a great big baseball stadium, the surface area, the gates to exit are not as great as our Olin lecture hall. And we're going to talk more about this as we go on in the course. The fourth real way to think about this is just the structural integrity of the plasma membrane. So this is like blowing up a balloon. More and more, keep adding air into a balloon, and the darn thing gets big. And I don't know if you've ever really inflated a balloon, but you start squinting because you're waiting for this thing to explode or pop. Well, the same thing is going on with the cell membrane. The structure of a cell membrane is not fundamentally different in little cells and bigger cells. It's pretty much the same stuff. And so as you get big, really big, there's a problem that maybe it's going to rupture, especially if it's an isolated cell like a red blood cell. Sometimes cells, or actually most of the time, they're packed in together. So it's a bit like buying, grocery cereal off of the shelf when we used to have well-stocked shelves at a store. So you might have to slide the box out because the other boxes around it are all pushing it and supporting that one box of cereal. Well, that's cells. They're supported by their neighbors. This structural integrity, I'm saying, is a bigger problem if you don't have your buddies around you helping to support you. All right, so we talked about what limits cell size, and that's it. 4 different factors, and I really wanted to talk that through with you. Now that we know cell size is limited, we ask the question, are the cells of an elephant larger than the cells of a mouse? And the answer is no. So, how do you make a big elephant? More cells. That's the answer. More cells. Lots of cells. And so, when we've taken a look at animal evolution, we started out with some very, very simple things, like the cnidarians, we looked at sponges, and as the organisms get bigger, then we see more and more cells. And there are some advantages of having more cells. Let's go through them. First of all, you can be big without big cells, so you help with the problem of maximum diffusion distance. And therefore, critters can get bigger. Second, you can have different kinds of cells doing different things. We certainly do. So of all the cells in your body, of which the estimates vary, and each of us is varying in our own size, but you might have 50 trillion cells in your whole body. Now, just today, the government passed a $2 billion help or support for all kinds of different things in the nation. That was $2 billion. And I just said that you have 50 trillion cells in your body or so. So how much more is that? Well, I think right off the bat here that it's 50,000 more. So $2 billion times 50,000. Oh, I'm sorry, it's 25,000. 2 billion times 25,000 is $50 trillion. So, oh my goodness, you have a lot of cells. Out of all those cells, how many different types of cells do you have? And the answer is over a couple hundred, probably between 200 and 300. So that when you get really, really big and you have a lot of cells, you can have cells doing different things. And of course, we've already talked about muscle, but we've got nerves, for goodness sakes. You got skin cells, you got bone cells, you got blood vessel cells, so cells that line the blood vessels, smooth muscle forming the walls. In addition, you also have cells that make eggs and sperm. The cells that make eggs and sperm are called the germ cells. Everything else is called somatic cells, our somatic cells. So if I asked you what an egg is a germ cell. But if I asked you what that muscle cell was, the answer is a somatic cell. And that's it, guys. That's the very, very end of the information for the second lecture exam. So if you've got your lecture outline, and I hope you do, then make sure you're drawing a line across the page. I think it's just before we start talking about skeletons. So from that point on in the lecture outline will be lecture exam 4 information. Good luck.